Alright, here we go. We're going to finish up K and L in our molecular shapes. Okay? Now, SF6, S has 6 valence electrons. Fluorine has 7, but there are 6 of them. 7 times 6, last time I checked, was 42, plus 6 is 48, I believe. So, sulfur is going to be our central. I got to get 6 around here, so I'm going to start top and bottom. And then I'm going to kind of branch out here. So I've got my 6 fluorines around it, and remember I'm going to complete the octets of anything attached to the central atom. So as we go around, we have 6 fluorines. Once the octets are all complete, then we'll have 6 times 8, which is 48. So we actually have all of our electrons here. So that means we have 6 electron regions. That means that we are an octahedral. All of our bonds are identical. We have no lone pairs. So our molecular shape is an octahedral as well. Bond angles, octahedrals are restricted to 90 degrees for all. Okay, and then polarity. Well, sometimes polarity is easier to see if you draw it out. What you're going to have is here with the fluorines at all positions. And if you draw the lines, which I'm not going to do because that makes it look, well, I can't do it. It makes it look goofy. So what we have is a perfect octahedron, which means that even though our bonds are polar, the molecule is perfectly symmetrical. It has, you can't not draw a plane of symmetry. Symmetrical. So those two combined to give me a non-polar molecule, because polar molecules must have polar bonds and be unsymmetrical. Alright, then hybridization, we have 6 singles bonds. So we need 6 hybrids. So we start with an S, we only have one of those. 3 P's, we're up to 4, and we need 2 D's. So sp3d2. Okay? Alright, this is our last problem here. We have 6 valence electrons here. We have 6 for oxygen, so that's basically 4 times 6, which is 24. Selenium is our central atom. Our oxygens are attached. We're going to complete the octet of the species attached. So that gives us 24 electrons. And we got 24 electrons. All the sulfurs are happy. The oxygens are not. So, I mean, the oxygens are happy, the selenium is not. So what we're going to do is take a pair and donate it in. So what we'll do is we'll get the double bond selenium, oxygen, keep our lone pairs together because we have to have everybody's octet completed. Now this is one where you can have resonance structures, and again it doesn't matter because all we're moving is the double bond. We're not changing the region. We have 3 electron regions regardless of how we draw the resonance structures. Okay, and we'll do resonance structures on a separate round. So that being the case, 3 electron regions, that means that we're trigonal planar. Okay, because we still have 3 electron regions, they're all bonds, it's going to be trigonal planar for the shape. Now when we look at a trigonal planar, basically what we have is a triangle, so we have an oxygen, an oxygen, and an oxygen. Now this is going to distort the angles slightly This is 120, as is this one, but because the double bond is going to push more, it's going to increase it slightly, which means this angle here, again, starts off with 120, but will be slightly less than 120. It distorts it. It's not enough to distort it to mess up the symmetry. So we have polar bonds, but we have a symmetrical molecule. So these combine to give us a non-polar molecule. Okay, so I'm going to come over here to do hybridization because I accidentally went off the page here. So hybridization, so we're going to have 3 single bonds and 1 double. Now, what the double means is you have to have a P unhybridized. But the 3 means I need 3 hybrids. That being the case, start with my S, that's 1, but I need 2 P's, and I've got to leave 1 unhybridized. So my hybridization for this molecule is sp2. So we've completed this set.